Hi and Assalamualaikum. We are from Binti and today we would like to present about our group project AnalogSimulation. Alright, so this is my group members. So the first one is Nabila Binti and her matrix number is CE220087. And the second one is ARINA NAZIHAH binti Muhammad Nawawi and her matrix number is CE220067. And the last member is me, FARAFAQIHAH binti Muhammad RIZAL and my matrix number is AE220055. Right, so this is our project task. So the first task is we need to design circuit. Second task we need to do circuit analysis. And the third task we need to do simulation setup. And the last task we need to do simulation and show the result from the simulation that we do. For problem statement, the Zener diode's primary challenge lies in maintaining a stable output voltage across varying loads and input voltage. The problem statement involves addressing issues related to load regulation, line regulation, and minimizing the impact of temperature variation to ensure reliable voltage regulation in electronic circuit. For this project, we freely choose the value. So in this project that we choose for value R1 1.2K and for R2 11K. For objective, there are three objectives here. The first objective is to design and construct a Zener diode voltage regulator circuit that can provide a stable output voltage of 9 volts. The second objective is to determine the appropriate resistor value for the current limiting resistor R1 and the load resistor R2 based on standard resistor values. And the last objective is to maintain a constant voltage by regulating it at the Zener breakdown voltage, ensuring stability in electronic circuit.
Hi and Assalamualaikum, my name is Nabila. So this is the simulation of Zener diode. We use purpose.
Okay, so this is the simulation. We have the R1, R2, same. This is use battery and this is we use the sinusoidal voltage signal. So over here 1.2K, 11K ohm. This is also same 1.2K, 11K ohms. Let me play first. If you can see, if you use battery, you will get the static result, which is 9.17 volt, and this is like, it's like moving from negative 0.7 to 9.17 volt. So at first I use this diagram. At first I use this circuit, but then I changed the battery to V ini. Wait,
my name is Nabila. So this is the simulation of Zener diode. We use purpose. Hi and Assalamualaikum, my name is Nabila. So this is the simulation of Zener diode. We use
to sign generator properties. I change it because I need we need to see the waveform, right? So we need to use these sinusoidals to get the waveform. So this is the V in from here, and this is V out from here. Maximize. So as you can see, our input over here 43.6, 43.7 like that lah. So it goes like here, negative 43.6 and it's 43.7. This one also. This is the input because we put the value 43.7 based on the calculation that we get. The input supposed to be 43.7 if we use 1.2k and 11k as a resistor. Next, this is the V out. Okay, I'll maximize. Okay, V out we get 9.17 and negative 0.7 because this is in milli, right? If we put in volt, like negative 0.7. If I make it more clear, simulate. Okay, this is the V out. The red one V out and the green one is V in. If you can see, the answer is same as we do in calculation, which is we got the same value for V out. Over here 9.17. Then for the positive half cycle we got 9.17, and for negative half cycle we got negative 0.7 because this is a silicon, right? So this is the simulation, and we assume that we success to simulate the the circuit. It's same as we calculate and we get the same result. So that's all from me. Thank you.
Hi, Assalamualaikum. My name is Nurfarina NAZIHAH Binti and my matrix number is CA220067. Okay, I will explain to you. This part is RIZAL. So first 3.1 circuit design, we get V bigger than VZ is diode on. Okay, in produce, we got 9.1 voltage equals to 9 volt, and for current impedance we choose 28 milliampere, and for resistance we choose for R1 1.2 kilo ohm and R2 11 kilo ohm. Okay, for 3.2 circuit analysis, first step we remove a VZ voltage impedance and we redraw without Zener diode, and VZ equal V out. And so V out is equal to 9.1 voltage. And for step 2, V bigger than VZ is diode on. Since we don't know value of V in, just ignore V. So means that we replace VZ is 9.1 voltage and V out 9.1 voltage. So first step we use for find V1 we need to use Ohm's law, which is I2 equal to V out divided by RZ. So R2, and we got 9.1 voltage divided by 11 kilo ohm. And first I1 we got I1 equal I2 plus IZ, which means 0.83 milliampere plus 28 milliampere, that we got 28.83 milliampere. For find V1 is equal I1 times R1 28.83 milliampere times 1.2 kilo ohm, and we got for V1 34.6 voltage. Okay, for step 3, we must apply with KVL. Means look at this circuit. We got negative V in plus V1 plus VZ equal to 0. So we change V in equal to V1 plus VZ, and we got 34.6 voltage plus 9.1 voltage, and we get 43.7 voltage. Okay, for step 4, we need to prove that V in is correct. Which is for we want to prove V in is correct. Means first we use voltage divider rule. So V equal R2 divided by R1 plus R2 and times V in. So we got 11K divide 1.2K plus 11K times 43.7 volt. So we got 39.4 voltage. So V bigger than VZ. Is diode is correct. So we prove that V in is correct. Okay, for the last step, we need to find output voltage waveform. So how we need to find? Which is first look at this during positive half cycle diode reverse bias. So we got V in 43.7 voltage like before we calculate before this. And for the negative high cycle, we got negative 43.7 voltage. It's diode forward bias. So look at V out, we got 9.1 voltage, and V out is V out silicon is 0.7, so we got negative 0.7. So that's all from me. Thank you.
For, for conclusion, we can make conclusion that the objective are fulfilled. The input voltage and load resistor conditions are fixed, allowing the diode to be parallel to the output voltage. The circuit maintains constant voltage by regulating it at the Zainal breakdown voltage, ensuring stability in electronic circuit. Future work will vary input voltage and monitor output voltage to assess stability and efficiency. Investigation will also explore the effect of voltage variations on current flow and power dissipation, providing insights into efficiency and thermal performance. So, so that's all from us. Thank you for listening.